Hi everyone, we're going to look at some additional examples of retrosynthesis in this particular video. So we have the starting material and the target here. So starting material and we have the target. And right off the bat, I'm essentially going to identify if there's a change in the carbon skeleton. As you can notice, my starting material has 4 carbons, while my product has 6 carbons. Okay, so there is a change in the carbon skeleton. So add 2 carbons. And there's a change in the functional group also. The functional group in my product or the target here, this is an epoxide, and the starting material is an alkyl halide. So I have to convert an alkyl halide to an epoxide. Now, epoxide, in some sense, is an easy functional group to work with, or at least to approach the problem, because we've learned limited reactions that give us epoxides as products, right? So to make an epoxide, one reaction that we know of is the epoxidation of, and so it's not just the name of the reaction, but it's like, okay, what is the precursor? What do we make an epoxide from? So epoxidation is done on alkenes, which means if I have an alkene, I should be able to convert it into an epoxide. And with the epoxidation reaction, recollect that all that happens is a double bond is converted into the epoxide. So that means a precursor, right, or the intermediate prior. Now I'm calling to the intermediate, but it's not an intermediate in the sense of a reaction mechanism. We are talking about an intermediate product or an intermediate compound here. The precursor to that epoxide should be a 6 carbon chain molecule where there is a double bond between carbons 5 and 6, because that's where the epoxide is. Okay, and epoxidation can be done using MCPBA. This is a classic reagent for doing an epoxidation. So that means if I have an alkene, a 6 carbon alkene, that can be converted into that epoxide product. Okay, so that's good. So we're one step backwards now. Okay, now the question is, okay, if I have an alkene, 6 carbon alkene, and we have a 4 carbon alkyl halide, can we add alkene, like double bonded carbons, to something? Have we learned of any reactions like that? And the answer is no. But what we know is we can add triple bonds, we can add alkynes. So maybe we should add an alkyne first and then convert it into the alkene. So one possibility is that this alkene could have, or this alkene can come or can be synthesized from a 6 carbon alkyne. So I'm going to draw a 6 carbon alkyne. So there we go. We have a 6 carbon alkyne now. 1, 2, 3, 4, 5, and 6. Okay, so that alkyne, that alkene can be produced or synthesized from this 6 carbon alkyne. And alkynes can be converted into alkenes by 2 approaches, using the sodium metal reduction, sodium in liquid ammonia, or you could use a hydrogenation using a Poisson catalyst, like a Lindlar's catalyst. In this particular case, we're going from a terminal alkyne to a terminal alkene. So the method is irrelevant because they will both give us the same product. So I'm going to write both of them down. So you could say that this can be done using hydrogen gas and Lindlar's catalyst, or you could use sodium with ammonia liquid. They will both give us the same product, that alkene. Okay, so now we're one step back again and we have an alkyne. And the reason why we converted or we chose to make that alkene from an alkyne is because the alkyne can be synthesized from an alkyl halide by doing a substitution reaction. So now if you look at it, we have a 4-carbon alkyl halide, we have a 6-carbon terminal alkyne. So to convert that alkyl halide into this alkyne, what I can do is I can react. We're going to break here. That's the bond that we're disconnecting, or that's the bond that we're trying to form from here. So I can use sodium acetylide. Again, 2 carbons comes in as an alkyne. The acetylide brings in that triple bond, and a solvent for this would be THF. So this is an SN2 reaction. So we can start with an alkyl halide, bring in carbons 5 and 6 as an acetylide ion. And if we're basing our synthesis on first semester of organic chemistry, then the acetylide is the only way that we can bring in carbon atoms, extra carbon atoms, the synthesis, the method that we've learned of. So anytime you see extra carbons added, think about acetylide, which means you must have an alkyne at some point in your synthesis. The alkyne has to be like one of the intermediate products. And from there, you will proceed by doing other reactions. Okay, so that's another example where we worked backwards. Let's look at some other examples here. Sorry about that. Okay. Let's look at another example. And what we're going to do in this example, again, this is retrosynthesis. We're going to convert this alkene, that's our starting material. Okay, that's our starting material. We're going to convert that alkene into an aldehyde. There. Okay. Now, again, start off by identifying if there's a change to the carbon skeleton, and clearly there is. My starting material has 4 carbons. So my product has 5 carbons. Okay. So that's sort of odd, and there's a reason I chose this to show you how that would be done. Okay. How could you add just 1 carbon? Now, once we proceed through the second semester of organic chemistry, you will learn more reactions, a lot more reactions that can probably do this. But so far, again, we are limited. Okay, but again, what we have to do here is we have to add 1 carbon, and our product here is an aldehyde. And this aldehyde has to be synthesized from an alkene. Okay. Now, what complicates this sort of problem, this synthesis problem, is that we're only adding 1 carbon. And as I mentioned previously, at this point, a good way to bring in carbons is using an acetylide. Okay, using that sodium acetylide. But if you use that, then the minimum number of carbons that you're bringing in is 2 carbons, because that has 2 carbons in it. Now you can use a longer acetylide, right? Because realize that if I want to bring in just 2 carbons, I can use sodium acetylide, just the simplest of these acetylates. Or if I want to bring in more number of carbon atoms, I can use another acetylate. So I can use this, but this carbon, instead of having a hydrogen attached to it, it could have a carbon chain, whatever number long. It could have like 2 carbons, 3 carbons, 10 carbons, whatever that number would be. So I'd be able to bring in any number of carbon atoms that way. Okay, but in this particular case, we have to just bring in 1 carbon. And that, like I said, it's not possible. So what we can bring in is 2 carbons. But we're working backwards here. So let's think about, okay, how can we synthesize aldehydes? So we can only bring in 2 carbons, but we only need 1 carbon in our product. Is there a reaction that we learned which actually results in the loss of carbon atoms, where you can break up a carbon chain and maybe cut short on the number of carbon atoms? And if that reaction makes an aldehyde as a product, then it's a win-win situation, right? So, I mean, eventually, right, luckily there is one reaction that does that, right? Because we can synthesize aldehydes from or using the ozonolysis reaction. And what we know is an ozonolysis is done on an alkene. And what it does is it would split that carbon-carbon double bond. At the pi bond, it would just cleave it. And it would give you an aldehyde product if you have a suitable alkene to start off with, because you could also get ketones as products. So in this particular case, looks like I have to bring in 2 carbons, and then I'm going to lose some. So one possibility is that I have an alkene, which is this guy. Let's say if I have this alkene, and if I do an ozonolysis on that, so low temperatures, and then quench the reaction with dimethyl sulfide. Because if I do this reaction, have 1, 2, 3, 4, 5, and 6 carbons here, but the ozonolysis reaction, what it's going to do is it's going to break or cleave here. And it's going to add an oxygen on either side to those double bonded carbon atoms. So I will get my product or the target here. This half is going to give me the target. So this seems like a reasonable molecule. Now, you can argue that, yes, this does not have to be 6 carbons, right? It could be 7 carbons, it could be 8 carbons, and you would still break off to give that same molecule. That is correct. But then on the other side, then we are losing too many carbons, right? So that's a waste. If you think from like an atom economy point, right? Okay, how many atoms were there in your starting material for this step versus how many atoms actually end up in the product. So in this particular case, we have 6 carbons. Our product has 5 carbons. So we are losing 1 carbon. Okay, that's less waste. Compare it to a situation where I have this with maybe 2 more carbons to it. If this undergoes ozonolysis, it is still going to give me that same product. But on the other side, I'm going to be losing, or I'm generating a byproduct or a side product which has 1, 2, and 3 carbons compared to this where it's just 1 carbon. Okay, so either one is a reasonably correct answer here, but this one minimizes the number of carbons that we are losing. So for that reason, I'm going to go with this. Maybe I'll also show you how to get to something like this. And again, I just chose this to be 2 carbons, but please realize that it can be any number of carbon atoms here. Okay, so let's go with this option here. So if I have this alkene, okay, now the alkene, since we are adding some carbon atoms, the alkene, we cannot just add double bonds, so we have to add it as a triple bond. So that means a reasonable starting material for this is going to be an alkyne. So we have 1, 2, 3, 4, 5, and 6. And this alkyne again can be reduced by hydrogen and Lindlers, or you could use sodium and ammonia liquid. Either one of those is going to give me this alkyne as the product. Okay, and so that's the alkyne that we need for moving forward. So if this is confusing, let me take those away. That's the alkyne that we're talking about. This alkyne can give us that alkene that we want moving forward. Now, to synthesize this alkyne now, we are adding 5 and 6 because this is a 4-carbon fragment. So this can be synthesized from, again, as we did in the previous examples, you can bring in Br plus the acetylide. So you can bring it in as an acetylide. Okay, that's the 2-carbon fragment. My 4-carbon alkyl halide is here, and there's my carbons 5 and 6. These would react with each other in presence of a polar aprotic solvent, to give us a substitution reaction. Right? The nucleophile attacks, the halogen leaves. This is just the number of the carbon atom. Okay, and then from that alkene that we have, which is our starting material, we have to make this alkyl halide, which is the less substituted alkyl halide. So we can do that using HBr and ROOR peroxide. So that will give me that. Okay, so that will be the route to go to that product. Now, let's say if I don't want to think about atom economy, I'm not bothered about how many atoms I lose, and I want to add like any number of carbons to it. That change would happen here, because instead of this sodium acetylide, if I choose sodium acetylide, which has this R group or the CH2R group connected to that carbon, then my product resulting from this is going to be that, where I have that other fraction connected to that carbon now. And then from here, I can do these same reactions and it would give me that alkyne. Although, okay, now I guess this is where it gets tricky. The alkene and the alkene that I have drawn here is a trans alkene, which means I cannot do either of these reactions now. I take that back. The only reaction that would work here is the dissolving metal reduction. So the sodium and liquid ammonia, that would give me the trans alkene. But if I did the hydrogen with the Lindlar's catalyst, it would give me the cis alkene. And when you do the ozonolysis on it, it's going to still give you that same product. So I guess it is irrelevant which reagent you use here, unless the stereochemistry of this alkene matters, if this is important in what you're going to achieve with that. Okay, so that's those are some additional examples of retrosynthesis.